Welcome back to the channel. Today we're going through exercise 1.41 from the Art of Electronics. In this exercise, we need to design a high emphasis filter with the response as you see on the screen now. In this exercise, we'll break down the concepts for the high pass filter, a potential divider, capacitive reactance of a capacitor, and how we can combine them to produce the response that you see on the screen. So let's get started. So the filter characteristics, first of all, so let's analyze the question. You have a 50% gain at DC or 0 Hz. And then as you go up in frequency, as you can see on the x-axis over here, the gain of the filter or the output of the filter starts to go closer to 1. And we have some cutoff frequency denoted over here, which would generally be the 3 dB point. And 3 dB point for a voltage output would be 0.71 approximately. So to summarize the filter characteristics that we're looking at, we've got a gain of 1 at high frequencies. So that is basically a high pass filter. We have a gain of 0.5 at DC. So that is basically a potential divider. So looking at a high pass filter first, we have been through a design of high pass filters in the past on my channel. So feel free to check that out as well. But you have a series capacitor with a parallel resistor. Basically the capacitor is series with the load and the resistor is in parallel with the load. And in a potential divider, obviously you've got two resistors. If ignoring the load, you're basically splitting the supply voltage with proportion of these two resistors over here. For the high pass filter, we can calculate the cutoff frequency with this equation on the screen. So that's 1 over 2 pi RC. R being this resistor over here and the C being this resistor over here. On the question, we have omega naught, which is equal to 2 pi f. The potential divider equation, or the output from a potential divider, can be calculated with this equation over here. So R6 is this bottom resistor and R7 is this top resistor. For this equation, obviously we are ignoring R4 and R5. And in the question, we have a gain of 0.5. So what that means is that both of these resistors will need to be equal value. So combining the two circuits that we've just looked at, we can end up with the following circuit. So we have a potential divider with these two equations over here. So if I set the value of those two resistors to 1K equal, that means that the output at DC will be equal to 0.5 volts over here. Basically ignoring this load and ignoring the source resistor as well. Because the impedance of the capacitor for DC is very, very high. So we can ignore this capacitor for DC case. Now, as you start to increase the frequency, the capacitor, the reactance of the capacitor or the impedance of the capacitor starts to get smaller. So the combination of these two components starts to become smaller. And if you look at your potential divider equation, R1 will take a larger share of the voltage source, which is coming from here. So as the frequency goes up, the output voltage will also go up. So we've got a high pass filter, and for a DC case, we have a gain of 0.5 with these two resistors. So this circuit is basically what we need to answer the question. On the next slide, I have a plot of the filter response. So ignore the dotted line, which is the phase response. The solid green line is basically the amplitude response of the filter. As you can see, you've got a gain of 0.5 at DC, and as you go up in frequency, the attenuation reduces, so your gain is getting closer and closer to 1. And this is exactly the type of response we wanted from this filter as asked by the question. But how do we calculate the resistor values? So first of all, 3 dB point is approximately 0.71. So if you wanted to set your 3 dB point at a particular frequency, what you can do is use the equation that's shown on the screen here, which basically tells you 0.71 is equal to 1, which is your voltage source, so a normalized voltage source over here, times R1, which is the bottom resistor down here, divide by R1, which is that resistor, plus the parallel combination of the capacitive reactance and the resistor R4. And the capacitive reactance can be calculated with this equation over here. So as you can see in this equation, you can bring in everything that you need to work out this equation. Obviously, first of all, you would want to calculate the DC gain. So if your DC gain was above 0.71, obviously it wouldn't be possible to do this filter anyway. But let's say we're setting the DC point to 50% as in the example, then you can calculate the DC point with this equation over here. So you've got the bottom resistor divided by the total resistance of the top and the bottom resistor. Now to set the value of this resistor, you want it to be at least 10 times the value of your source resistance. So in our case, we're not being given a source resistance, and you want it to be at least 10 times smaller than your load resistance. So if you find some number in between those two values, if possible, then that's what you would go for. So then you can set the total combination of the resistor as that value. Now for step 2, obviously you know FC because that's one of your design parameters, and you know the resistance values for the bottom resistor and the top resistor. So in this case, I've denoted it as R1 and R4. That's because of the model that I pulled out from LT Spice, but obviously you can call it what you like. What you need to do is rearrange this equation to get the unknown parameters by itself. So in this case, it would be C. So if you place this inside here and then rearrange the equation to get C by itself, you can calculate the value of C that you need to achieve 0.71 at the frequency that you need with the value of resistors that you have set. On the screen now, I've just gone through that calculation. And basically, so I've got the top and the bottom resistor as equal values, and then I've got a capacitor value over here. And here is a calculation for the cutoff frequency from these two numbers. In here is the rearranged equation. So you can see C3 is basically your bottom resistor and C2 is your top resistor. 0.71 is the required gain at the 3 dB point. Now I can basically change the value of this resistor to get the cutoff frequency that I want. So let's go for a 100 nanofarad capacitor and R1 and R4 equal to 10 kilo ohms. So let's see how that circuit works. Obviously, I'm going to delete the circuit I have on this side. You have R1 on the bottom. Obviously, we set that to a value of 10 kilo ohms. We set this to a value of 10 kilo ohms and our capacitor value was 100 nanofarads. That should give us a cutoff frequency at the 3 dB point of 230 Hertz. So let's simulate this. I'm doing an AC analysis on this. So that's a linear sweep from 1 microhertz to 10 kilohertz. And if I press play on this, so if I press play in this, I get the filter response for this filter that I've got on the screen now with a load resistance of 100 kilo ohms. Now with a cursor, I can show you the 3 dB point. So you got dB on this side over here. And if I drag that down to roughly 3 dBs, you can see that the cutoff frequency is 246 Hertz. And our linear point is approximately 6 dBs, which is half. But if I put that into linear to make it easier to read, you can see that it's 0.5 volts roughly, but just slightly below. And that is because of our load resistance. If I was to basically change this to 1 mega ohm load resistance, you can see that our DC point will be a lot closer to 0.5 volts because the load is not affecting the sensor that much. This is the main reason why you would want to select the impedance of this circuit to be at least 10 times smaller than the value of your load, so that you're not affecting the response of the filter too much when the load is connected. Now there may be a neater solution than this equation here. If you do know it, please let me know in the comment section below. So thank you for watching today. Don't forget to like, comment and share this video. And if you want to see more videos on Art of Electronics, press the subscribe button. Bye for now.